Welcome to Electromagnetics playlist. I, Professor Irej Dolakia, is going to explain you Ampere's law in this session. So first, to understand Ampere's law, I'll explain what is the basic law which is there with Ampere circuit, and then I'll explain you few cases where how to apply Ampere's law, and at the end I'll explain you how we can have calculation of magnetic field intensity for straight wire by using Ampere's law. So let us begin this session with what is Ampere's law. So see, Ampere's law explains you line integral of magnetic field intensity around closed loop is equal to total current enclosed by that loop. So let me write that first. So see, Ampere's law explains line integral of magnetic field intensity around closed loop is equal to total current enclosed by that closed loop. So if you want to write that by formula, then we can say line integral of magnetic field intensity over a closed loop, that will be equals to total current enclosed by that loop. So this is for closed loop, right? So this is Ampere's law. Now let us try to understand this with some basic understanding, right? So here, if I give you a wire, right, and through this wire, if I say current is passing and that current is I, then what will happen here? There will be magnetic field. So you can see magnetic field, and in previous session I have explained Biot-Savart law. So magnetic field will be as per right hand thumb rule. So, or one can say law of screw. So direction will be like, see, if current is moving in this direction, then you will have to rotate screw in clockwise direction, anti-clockwise direction, right? So you can say direction that will be as per right hand thumb rule, it will be like this, right? Now if you do line integration of this magnetic field intensity, then that will be total current passing through this wire. That is what Ampere's law. So for single wire, it is very easy to understand this line integration of this magnetic field intensity around this loop. But what if you have been given with multiple wires? Like, see, I'll give you multiple wires now. And if I say this is current I1, in this direction current I2, in this direction current I3, in this direction current I4. Now because of these wires, there can be magnetic field. So if I say in loop magnetic field is happening like this, right? So magnetic field intensity line integration, that will be total current enclosed in this loop. So I am considering this direction as per right hand thumb rule, right? So if you do this line integration of magnetic field intensity, then total current enclosed by this, that will be the Ampere circuit law. So over here, if you apply Ampere circuit law, right, for this case we can say integration, close integration of HDL, that will be equals to I, right? But for this case we can say this close integration of H dot dl, that will be equals to, in this direction we need to find current, right? So that will be I1 plus I3 plus I4. See, this current are in this direction, and I2 that is in opposite direction. So minus I2, that I need to say. So that is how we need to apply Ampere's law. Now this Ampere's law, that makes life easier for RF engineer, for antenna engineer, for electromagnetics, right? And how does it makes life easier? So let us try to understand that by a calculation of magnetic field intensity for straight wire. So if I give you a straight wire, then let us calculate magnetic field intensity. Now see, magnetic field intensity for straight wire we are deal with to calculate right now. So I'll consider few cases. Like see, I need to zoom wire first of all. So let us say this is a wire, right? And in this wire, there are three cases that we will consider for a calculation of magnetic field intensity. First case, that will be outside the wire, right? And in this wire, direction of current, that is in this direction. So magnetic field intensity, that will be inside the page as per right hand thumb rule, right? Like this. If you apply right hand thumb rule like this, then magnetic field intensity inside the page, that will happen. And if I say I want to this is axis of wire. So first case, that is magnetic field intensity outside the wire. Let us say this is distance r. So magnetic field intensity outside the wire, that we can calculate, where if I say radius of this wire, that is rho, then for outside the wire, this r, that will be greater than radius. Now see, for this only one thing that we need to do, just calculate line integration of magnetic field, that is equals to current passing through wire. And here we are dealing with to calculate total current. So if you see this case, right, where distance with respect to wire, that is r, that is given to us. So if you calculate this line integration, then that will be 2 pi r, right? So h into length, that is 2 pi r. So this hdl, that will be h into dl. This hdl, that is h into dl, and this length is 2 pi r. So we can say magnetic field intensity, that is I divided by 2 pi r. And if you observe the direction, then direction, that will be in the direction of phi direction, right? So as per cylindrical coordinates, we can say direction, that is there in the phi direction. So unit vector phi, that I am writing. In examples, I will show you how to calculate this phi direction. Now let us have second case. So for second case, on the surface, we are dealing with to calculate magnetic field. So let us say case 2. So for on the wire, we can say r is equals to rho. So in this case, magnetic field will happen due to total current which is passing through this wire, right? So here again, integration h dot dl, that will be again I, and here h and dl, you will be finding both are making h into, now integration h dl. So for this radius, now we need to calculate total length. So that will be 2 pi rho is equals to I, and we can say this h will be I divided by 2 pi rho. And again direction will be there in the phi direction. This is very important. It will be there in the phi direction. And for third case, inside the wire, we are dealing with to calculate magnetic field intensity. So where r is less than rho. So in this case, again same formula that we are dealing with to apply, h dl, that is equals to, now current enclosed will be different, right? See, in second case we have calculated at this distance where r is equals to rho. Here r is greater than rho. Now for third case, we need to calculate it for inside the wire where r is less than rho, right? So in this case, now current will change. Now I need to say that is I dash, and same thing will happen over here, integration h dl. So that will be h into 2 pi r. But what will be I dash? Now you see I dash, that will be total current into, now you see total current that is happening in total cross sectional area, and total cross sectional area of this wire will be pi rho square, and we are delivered to calculate now current for area with radius of r which is less than rho, right? So total current into surface area of this r radius, so that is pi r square, divided by surface area, that is pi rho square. So this is how we can find current passing through radius r over here, right? So that is I dash. And now you can have total magnetic field inside the wire, that is H is equals to, you can see this pi will get cancelled and this 1 r will get cancelled. So we can say this will be r into I divided by 2 pi rho square. Now see, here there is one thing that we need to understand. Outside the wire, magnetic field intensity, that is inversely proportional to r. On the wire, on the surface of wire, it will be constant I divided by 2 pi rho. Outside it will be I divided by 2 pi r. And inside the wire, magnetic field intensity is proportional to r. So if you showcase this with respect to distance, then it will give you better idea. Like see, over here we have magnetic field intensity, over here we have a distance. Now if I say this is what radius rho, so this is a region which is what inside the wire. So inside the wire, magnetic field intensity is directly proportional to distance r. So that will be straight line, you can see it will happen like this. So inside the wire, magnetic field intensity, that is proportional to r. On the wire it will be 1 by 2 pi rho, you can see, and outside the wire it will be I divided by 2 pi r. So it will decrease with respect to distance. So from here it will decrease with respect to distance. So one can see magnetic field intensity is proportional to 1 by r outside the wire. So magnetic field intensity inside the wire, that is proportional to distance r. On the surface of wire it is constant, and that is I divided by 2 pi radius of wire, and outside the wire it is inversely proportional to distance. See, this is how magnetic field intensity is there. So by using Ampere's law, we can easily understand this calculation of magnetic field intensity. I hope that you have understood this. Thank you so much for watching this video. Please do give your valuable suggestions. Definitely based on your suggestions in future I'll make videos which will solve your queries. Thank you so much for watching this video.